draining a cone. Water is drained out of an inverted cone with a height of 12 feet and a radius of 6 feet. If the water level drops at 1 foot per minute, at what rate is the water, in cubic feet per minute, draining from the tank when the water depth is 6 feet? Okay, well, all these words are great and all, but nothing can compare to the value of a picture when it comes to solving a related rates exercise like this. So let's draw a picture. We have a cone, an inverted cone, so it's something like this, going down like so. Okay, there's a nice cone. Upper radius we decided that was given to be 6. I won't put the units into my illustration here. And maybe the height of it here we can put as 12. And what's happening is the water, maybe there's the water level. Let's call this distance that the water level is y. You could also call it h for height. I mean, pick any variable you would like. And let's call this distance here the radius of just the water part. Rather than calling it r, I'm going to call that x. But you could certainly call it r. Call it whatever you want. So this distance here is x, just going across the top of the water. And what's happening here is there's some kind of hole in this here at the bottom, and we have dv dt happening. Well, and it's asking at what rate is the water draining from the tank? So that's what we don't know, but we're also given that we have some dy dt, because this water is going down at a constant rate, -1 foot per minute. I'll use -1 because it's going down. You can use negatives for things that are getting smaller and decreasing, and positives for things that are increasing. Although it wouldn't be the end of the world in this example if you didn't include that negative, right? So what's going to happen is we'll get a negative dv dt for an answer saying our volume is decreasing. Well, we already know the volume is decreasing because it's draining. So if you forgot this negative, you would just get a positive dv dt. It'd be the same number, and you just have to make sure that you say, yeah, it's decreasing. The volume's decreasing. Okay, well, let's just stop for a second and think about this. This height is decreasing at a constant rate. So when the water's way up here at the top, right, and this whole thing is full of water, and this is going down at a constant rate, well, you have a whole lot more water going out per minute than when it's way down here and it's just going down at a constant rate. So say we're looking at over 10 seconds. When we go down 10 seconds up here, it has to squeeze out that much water, which is a ton of water. So dv dt must be really high at first when the volume of the water is high, or when the height of the water is high. But when we're down at the very end and we're down here just at the very bottom, the water's going down, but it only has to squeeze out this little bit in the same 10 seconds or whatever. So dv dt is going to be much smaller at the end of the time period that this problem covers than it was at the beginning. So it's just interesting to kind of think that through a little bit and realize that dv dt is not a constant in this case, even though the height of the water going down is a constant. Okay, so let's identify our givens and our goal. So we have given and goal. Okay, so what's given? Well, and we're really just looking at the rates here. We have dy dt is -1 foot per minute. This just helps us keep track of what we're doing. The givens are good, but the goal is what to really focus on. The goal is dv dt. Well, we just decided that it wasn't constant, so when? Well, it looks like when the depth is 6 feet. So when the depth is 6 feet, when y equals 6. Well, there are steps for these, so let's just check in real quick with our steps. Okay, step 1 was to understand the problem deeply and sketch a diagram. Identify the variables, list your givens and your goals. So we have done that. Check. On to step 2, write a single equation, right, that relates all the various quantities. So, okay, back to our example. The quantities we want to relate in a single equation are x and y and volume. Okay, because we want to eventually get v and dv dt and dy dt in the same equation. Okay, so the volume of a cone is 1/3 pi r squared h. But in our case, instead of r we have x, and instead of h we have y, so I'll rewrite this. 1/3 pi x squared y. And you may be asking, do I need to know the equation of the volume for the cone? Yes. Make sure you know that. I would argue that it's not entirely hard to memorize, right? It's just the equation of the cylinder, pi r squared h, divided by 1/3. So if you know the volume of a cylinder, which you should, you can just divide that by 3, and you have the volume of a cone. Okay, well, the problem here is that we have two variables happening, but we only want one variable. And the way we do this is an old trick from geometry known as similar triangles. And this seems super obscure, but it shows up all the time in related rates problems. So what are these similar triangles? Okay, well, here I've taken a cross-section of our cone here, and you can see the similar triangles forming. Where are they? Well, this big one is one, right? And then the small one is another one. So these are similar triangles that are inside of each other, right? You may have learned this theorem somewhere back in geometry with two different kinds of two separate triangles that were similar, but in these they're always going to be embedded one inside the other. Okay, so let's label what we have here. We have x and y, and then our distance up here is 6, and our entire distance from top to bottom of this thing is 12. And the way similar triangles work is they essentially compare one side to the other. So what this says is x is to 6 as, so we say equals for as, y is to 12. So we've just said that since these are similar triangles, one inside of the other, the ratio of x to 6 must be the same as the ratio from y to 12. And now we can solve for one variable in terms of the other. We've related these variables. Now, which variable do we want to work with? Since I'm given dy dt, I'd rather have all my variables in terms of y. So I'm going to solve this thing down here for x, so I can then substitute for x and get only y's in my equation. So if we solve this for x, we get x equals, multiplying up by 6 and simplifying, 1/2 y, and in it goes into our x. Okay, so plugging that in, let's clear out some room here. V now equals 1/3 pi. Well, we decided x was 1/2 y squared times y. Okay, now we're making progress here. Okay, so volume then is okay, so 1/2 squared is 1/4 times 3. We have times 1/3 is 1/12 pi y cubed. And now we can take the derivative of both sides with respect to time. Going back to our steps here, where we are now on to step 3, use the chain rule to differentiate both sides with respect to time. Okay, no problem. We'll just take d by dt of both sides, d dt. Okay, so what do we have? So this tells us that dv dt is 1/12 pi 3y squared dy dt. That's our chain rule step. Well, I kind of scrolled past it here, but if you recall, dy dt is negative. Maybe I can keep this all on the screen. Dy dt was negative 1 foot per minute, and our goal was to find dv dt when y equals 6. So we can plug all this stuff in right now. So dv dt at y equals 6. So how about we say evaluate it at y equals 6 gives us, okay, so 1/12 pi times, well, okay, so we can simplify 1/12 with that 3 up there to just give us 1/4. So let's try to keep this as simple as possible. Okay, so y squared is 36 times 36, and dy dt is negative 1. So this all comes to negative 9 pi cubic feet per minute. So there's our answer, and we'll write it nicely here. And I do recommend leaving it in terms of pi unless for some reason the exercise specifically says not to. So we'll write it nicely. We'll say volume is decreasing at a rate of 9 pi cubic feet per minute. Just making sure our units match everything. Minute. Well, the rate was given, everything's given in feet per minute, and the example, if you recall from the beginning, asks us to find dV/dt in cubic feet per minute. So there you go.